Today's artificial limbs are a far cry from the wooden leg of yesteryear. They look very realistic. And thanks to advances in prosthetic technology, artificial limbs function more and more like the real thing. They start by measuring the amputee's stump, what doctors call the residual limb. First, they measure the circumference at different points. Then the diameter at different points. They protect and lubricate the residual limb by coating it in petroleum jelly. Then they immerse it in algin, a gelatin-like substance that comes from algae. After about 5 minutes, they remove the residual limb. The algin has already begun to stiffen and maintain the limb's shape. A couple of hours later, it's stiff enough to be used as a negative mold. They pour in plaster of Paris, then insert a metal rod. The rod is what will later allow them to mount the dried plaster to work on it further. The plaster takes about an hour and a half to harden. They cut off the algin. Then, using sandpaper and files, they refine and smooth the surface. This plaster copy of the residual limb will now be used as a positive mold to cast the artificial limb. Often, they use a different technique to make the positive mold. They build a negative mold first using strips of plasterized cloth, much the same way they make a plaster cast when you break your leg. Then a scanner takes a detailed three-dimensional reading and programs it into a computer. A technician then makes any necessary modifications. They put a plaster block on a cutting machine. The computer guides the blade to carve out the positive mold. With either technique, once the positive mold is ready, they can make the artificial limb. The process they use is called lamination. First, they cover the mold in fabric socks. Some made of nylon, others of a material that contains fiberglass. They layer 6 to 10 socks in all, depending on how rigid they want the artificial limb to be. Then they coat the socks with a liquid resin made of either polyester or acrylic. Here they're using acrylic tinted to look like Caucasian skin. It's important to ensure the surface is evenly soaked. It's a meticulous process that takes about an hour. The acrylic solidifies in about an hour. Polyester takes about 12 hours. They then break the plaster mold inside, leaving a durable plastic shell called a socket. That will be the basis of the artificial limb. The socket connects to another plastic shell containing the mechanics. Or, like this artificial leg, the mechanism can be modular and covered in just a skin-colored foam. If the muscle at the site of the amputation still emits a good electrical signal when contracted, the patient can get a myoelectric prosthesis. It has an electrode that captures and amplifies the signal, triggering the artificial hand to open and close.
All consumer products are packaged, and the making of these packages starts with the burning of an aluminum plate like this one. This animation illustrates the burning process, the transfer of an image onto an aluminum plate. The plate is placed onto a cylinder, and using a laser, the burning begins. The image appears in 6 minutes. This plate will make the printing impressions on packages. The laser which did the burning has to be perfectly calibrated using this test plate. The plate is now ready to make impressions via the offset method. Printing involves ink, and it requires selecting the right one. If the desired color does not exist, it has to be made up from a mix of various other colors. An ink trial is done with a spatula. And using this small manual press, color ink tests are done. The ink is spread onto paper, and the color compared with the one called for by the customer. If the two match, the presses can be started up. This is a 6-color offset process printing press with a 72 by 108 centimeter capacity. The press is fed by a suction and friction process, devouring 8,000 sheets an hour. Now the printing plate is placed onto the press cylinder. This plate will contact inking rollers of the ink reservoir. To prevent it from drying, ink viscosity is maintained with this oscillator. The press starts up and reaches a production rate of 8,000 impressions in 60 minutes. The press comprises individual color printing units. The paper sheet passes from one unit to another, receiving a new color at each step. Here they register the colors, that is, the quality of the superimposition of the different colors. The final step is the folding and gluing of the boxes. This grooved plate makes folding point marks on the carton. And this machine does the cutting, the embossing, and stripping of the sheets at a rate of 6,000 an hour. The cutting die cuts the carton sheets and, together with the grooved plate, makes the folding joints. This sheet is slid behind the cutting die to equalize the cutting of the sheets. This enormous pile of 3,000 sheets is ready to be cut. The embossing press feeder handles between 6,000 and 8,000 sheets an hour. Rollers guide the sheets in the direction of the press. And here, the sheets are embossed by the machine. The precision of the embossing is then verified. Next comes the cutting of the sheets. This goes on at 8,000 an hour. The cutting unit strips and removes the unnecessary pieces, and the carton scraps are sucked up for eventual recycling. The scraps can also be cut away manually by using a hammer. And the carton end pieces are sent off for recycling. All that remains is the assembly of the packages. This high-speed gluing unit can make up 30 to 40,000 per hour. Gluing begins with the folding of the sheets, following the folding marks. The sides of the form box are then glued together. An average of between 5 to 8 steps are needed to fabricate a packaging box. Every day, this plant produces between 1 and 2 million boxes, requiring almost 4,000 tons of cardboard annually.